Hello everyone, this is the video lecture of section 1.3 of Math 4500, partial differential equations. Okay, so in this short section, I'm going to derive the PDE called linear transport equation or linear advection equation. Normally, deriving a PDE is not a job for mathematicians. Those are done by physicists or engineers, people who do application area. Normally, mathematicians take those PDE system and analyze it. Okay, investigate the solutions and how to find solutions, existence, uniqueness of solutions. But sometimes mathematicians have to also derive PDE from their own work, other areas. So I think it is important to see at least a few derivation of famous PDE. So this is about linear, so one-dimensional case. Let's say you have a flow of either liquid or gas, probably a gas, through a thin pipe, okay? Then the gas is moving with certain velocity. This is velocity. So this is along the x-axis. Let's say this is 0. Let's say this is x1 and x2. Okay? So this is the velocity of gas. The velocity of certain gas in the pipe at x, point x, space point x, and time t. All right. Obviously, as this is changing over time, also changing over position, and also we can think about this rho of xt as the mass density. So how much of mass per unit length do you have at certain point and time? It could be kilogram per meter, or gram per centimeter, or whatever. Okay. And v of t at x at time t. I'm going to call it at xt, okay? In short. V of t, v of xt, also velocity, the velocity of the gas. The velocity of the gas, at the time, meter per second or centimeter per second, depending on the unit. Now, we're going to derive mass flux. Okay. Now, what is mass flux? This is, if you think about some imaginary membrane here, let's say there's a membrane here through a certain point. Then if gas is going like this, you can measure how much of mass going through a certain membrane, imaginary membrane, let's say, certain cross-sectional region per unit time. That would be mass flux. Okay? Mass flux is the rate of mass flow, okay, from left to right, okay? From left to right of the gas. So that would be kilogram per second or gram per second. How much of mass going through certain cross section? At x and time t, obviously it can change over position and time. All right. We're calling mass flux. All right. Now, how I'm going to derive mass flux. Now, think about this. Okay. Let's say you're following certain small block of mass of gas. Okay. This is x. Let's say x plus delta x over a short period of time. Okay. Over t to t plus delta t. Okay? At t. At t plus delta t. So supposedly delta t and delta x are very small. Alright? Then this is delta x. Right? Then your velocity, because it is very small, your velocity is rate of, this is almost same as delta x over delta t, right? So this is over a short period of time. A mass which was over here at time t will be moving to this position, delta x further. Okay? Now here we are assuming that your velocity is positive, meaning from left to right. Okay? If velocity is negative, then this will be located over here. Okay? So, your delta x will be approximately velocity of xt delta t. Now, what is the mass on this short segment? Alright? And mass will be mass, total mass, delta m. The mass within this short segment, length of delta x. What is how much is the mass? Delta m, which is rho of xt times delta x. This is a linear mass density, mass per unit length, times the length. Okay? Of course, this is not constant. It is changing over time and position. However, when delta x is really small, this is almost a constant. So this is a linear approximation. Okay? Then, so the mass in the mass in this short section is the mass passed through this surface, cross-sectional surface here, during delta t's time, right? So our mass flux, which is delta m over delta t, will be approximated, what is it? Rho of xt delta x over delta and delta t. And what is it? Rho of xt delta x over delta t is v of xt. If you delta going to 0, if you take the limit, that will be exactly this value. So our mass flux turns out to be this quantity. Rho xt, velocity xt. This is mass flux at xt. At the position x, at the time t. That will be mass flux. From left to right. So which means that if this is positive, then you have a net flow from left to right. Through this cross surface, this much of mass going through per unit second, from left to right. If this is negative value, that means going to the left, right? Mass density is always positive number. Velocity positive means going to the right, plus negative means from right to left, all right? So you covered plus and minus both case. So now I will consider a mass going back to this inside this segment between x1 and x2. Okay? So mass in this section x1 to x2 at time t will be, when you're given linear mass density, the position integration of mass density will be your total mass dx for any given time. T is fixed. You're integrating with respect to x, right? By definition, linear mass density. Integration of linear mass density will give you total mass along a certain section of the pipe. Now, we are assuming that this pipe is impermeable, which means that your gas cannot go through the wall. There's no leaking, right? So, assuming that the wall of the pipe are impermeable, and that mass is neither created nor destroyed. So there is no chemical reaction that certain gases, combine to become a liquid or solid, so gas disappear. No, there's no such things. So no chemical reaction basically here. So gas stays a gas. So mass is conserved, right? Then, what is this? Rate of change of total mass in this little section of pipe. Total mass in this little section of pipe. Rate of change will be solely depending on how much you get in through this left-hand side cross-section per unit time, right? And how much going out of this through this right-hand side section, cross-section, right? So mass flux, how much get in per unit time? How much mass get in? Minus how much get out, right? So you can write this one because there's no creation. The only way mass in this section changing is how much going in, inflow, and how much going out, outflow. So that would be rho. So we learned that mass flux is this, linear mass density times velocity. So mass flux at x1 times t, vx1t minus x2t, x2t. Now this one already including sign. Imagine that both are going from left to right. Indeed, this is positive, positive. So I'm coming in this much, going out that much minus. What if V1 is positive, V is positive here, and negative at x2? Positive and negative. Minus minus cancels positive. Yeah, both coming in, right? Or velocity is negative here, positive here, negative here, positive here. You're losing here, also losing here. So this one considers, because mass flux is defined from left to right. So the sign of your velocity will control that. So you don't have to worry about the sign. This covers them. All right? So I'm going to call it equation 1. Okay? This is basically conservation of mass. Okay? The only way mass changes in this section is only from inflow and outflow, not through chemical disappearance or through chemical reaction, or introduction through chemical reaction. So now we're going to integrate with respect to t, with respect to. WRT stands for with respect to. With respect to t on this time interval from t1 to t2. Then you get, think about it. If you do time integral from t1 to t2, t1 to t2, the whole thing, right? dt, dt. The left hand side, t derivative and integrate, so you're going to get inside back. So this inside functions at t2 minus this inside functions at t1, right? So this will be rho xt2 yes, minus rho xt1. See? Differentiate and integrate. And this one is t1 to t2 rho x1t v x1t dt minus t1 and t2 t rho x2t v of x2t dt. Okay? Now, I can rewrite left hand side as x1, x2 of rho xt2 minus rho xt1. Okay? This one, why did I write this way? I shouldn't write it that way. Okay? Rho x1 t v. Okay, I'm going to take minus out. I could have written this way, minus. So take minus out, then t1, t2, switching this one, rho x2 t v of x2 t minus rho x1 t v of x1 t x1 t dt. All right. Now this one, rho x2 xt2 minus rho xt1. This one can be written as this t derivative integral. So I could write it as rho round of t at xt, right? That one's integral t1 to t2 dt, right? T partial derivative and t partial integral, right? We don't touch, this is not double integral, t partial integral. So x is fixed, so it's going to be this antiderivative at t2 minus t1. Yeah? Exactly. And this one, same thing, x2, here x1, so you could write this one as its integral of round, this one, round, round x of rho xt v of xt x partial of this quantity and x partial integral from t. No, this is x, I'm sorry, x partial. x1 to x2, right? x1 to x2. X partial derivative. So, antiderivative of this, which will be this, right? X partial. Its antiderivative will be this. From x1 to x2. Alright? So, both of them is double integral, right? Double integral x1, x2. t1, t2. Round rho, round t, xt, dt, bring over here. This is t1, t2, x1, x2, round x, roll of xt, v of xt, dx, and dt. Here dt dx. So this is iterated integral, right? With respect to t first and then with respect to x. With respect to x first, with respect to t. But in calculus 3 you learned that if your integral, the function is nice, smooth, continuous, right? Then this order doesn't matter. Both ordered iterated integral is just a double integral, same as double integral, right? So order doesn't matter, so I switch the order. Then they have the same interval, same. So this is basically you can combine it. Round t of xt plus round x of roll of xt v of xt dx dt. Of course, you can write this one as double integral, certain region d, right? Double integral d of this round roll, round t, round x, roll v, d, a. Then you have to do x and t, certain region d, right? From x1 to x2, t1 and t2. That region is d, right? But anyway. Now, equals 0. I brought this one, so this must be equal 0. So dx dt equals 0. Now, this is true for all x1 and x2 and t1 and t2. So in this case, for all rectangular region in xt. So double integral of some function is 0 over anywhere. That can happen only when this inside function is 0, identically 0. Otherwise, if this inside function is not 0 and continuous, a certain place is not 0, then over a very small region, that definitely will be some non-zero value, right? So this is true for every rectangular region, means that the inside function must be 0 everywhere. So we can conclude that. Therefore, this inside round roll round t. So I'm going to write a subscript. Roll sub t plus roll times v sub x equals 0. That's the what we call conservation law. One dimension conservation law along a pipe. Okay? All right. So we got conservation law. So that's the name of the PD, this PD, one-dimensional conservation law. So it involves two unknowns, right? That's a linear density function of x and t, and velocity function of x and t. So of course you cannot solve this when you're involved. You need more PDEs together with this. If you try to explain the behavior of gas in certain region, you need Navier-Stokes equation, system of Navier-Stokes equation. We need system of PDEs, but here we're going to consider very short cases. We cannot deal with this. Is more advanced. It's for more advanced course. All right. This is introductory course. We are going to consider special case of this conservation law. Special case. First case. If your velocity is constant, triple equal means that identically equal to C. Okay? It's not like if you do this, if you write this one, you'll be, this could mean two things, two different things. Maybe you're asking to solve this equation, or you're saying that your function is constant function, right? Your f of x is constant function, y equals 2, horizontal line. So in order to avoid that kind of confusion, if you want to describe this as a constant function, we use triple equal sign. Now if you don't use triple equal sign, that means this is an equation, right? You're supposed to solve for x. Only for few values of x, this will be true, right? So identically constant, right? Constant function. Constant. Then number one becomes what? Rho sub t. Now these are constant, you can be taken out. Plus c times rho sub x equals 0. Alright? So when your velocity is constant, this is what we call linear transport equation. 1D, linear transport equation. Okay? 1D linear transport equation. What about second case? Now, this is overly simplistic case. Okay? Everywhere, all time, your velocity is constant. It's not that interesting case, all right? More realistically, your velocity, think about it. If you have a very large density here of gas, smaller density, then definitely from high pressure region to lower pressure, the things will go to that direction, right? So the larger the difference of pressure, which is gradient, pressure gradient is larger than pressure gradient, the derivative of pressure over, with respect to length. Larger that, strong the wind, right? Just like atmosphere case. So your velocity at xt will be mainly affected by this distribution of the density. Alright? So our next attempt, more realistic one is, maybe this is some function of density, right? Where g is a function, where g is a differentiable function of one variable. Okay? Like rho square, sine of rho, whatever, right? Some function of rho. This is much better than this overly simplistic assumption. But if you really want to describe this, when there's a gas pressure, then also temperature increases. So you have to consider all kinds of this. You have to think about temperature changes, pressure. Or pressure is different from density. Even though your density is high, if it's very low temperature, then pressure is low. So you have to involve PD involving density and velocity, temperature, right? So that will eventually become Navier-Stokes equation system. Here, still better than this, but still it is a simplified assumption. That is the case. Then this equation becomes what? Rho. Look at this. Rho sub t plus g of some rho x t sub x equals 0. Then what is it? That is g derivative, right? No. I'm sorry. That rho t, rho times v, right? Rho times v, which is g of rho of xt. Okay? So I'm going to call it, this is f of rho. F of rho. X partial of this equals 0, where f of something equals f of, let's say u equals u times g of u, right? Rho times g of u, g of rho. Okay? We call it f of rho. Okay? So this is oh, I'm sorry. Did I say conservation? Conservation of mass equation. Sorry. Conservation of mass. And this is what we call conservation law. 1D. Conservation law. Okay? Very important hyperbolic PDE. This is conservation of mass. Okay? So this is a special case of conservation of mass in that regard. So one example, I'm going to finish this section with one example of conservation law. So, example 1. Let's say if your v of xt equals 1/2 of rho, so that means your velocity is proportional to the density, okay, a linear density, then number 1 becomes what here? Rho sub t, so v of t, 1/2 of rho square, right? One half of rho square of x sub x equals 0. So what is it? Chain rule. 2 to cancel. 2 times rho sub x equals 0. Right? So you get, this is 1D Burger's equation. So 1D Burger's equation is a very special case of conservation law, which is a special case of conservation of mass. So it's not really realistic, but it gives you some qualitative characteristics of, this equation. So this is used as a test problem when you develop some numerical schemes. You test with this simple. So that's why it's famous, important PD in hyperbolic PD, whatever that means. All right. Okay. So that's the end of the section 1.3. I spent enough time to show how you actually derive certain partial differential equations called conservation of mass. Okay? All right, so I'll see you next time. Bye.